Welcome to Torque and Rotational Equilibrium. We're going to talk, this is going to be a two parts of notes, so this will be the first set. An object will remain in rotational equilibrium if its center of mass is above the area of support. What determines whether an object will rotate when a force acts on it? Why doesn't the Leaning Tower of Pisa rotate and topple over? What maneuvers does a falling cat make on top of it to land on its feet? This chapter is about factors that affect rotational equilibrium. To make an object rotate or turn, you must apply a torque. Every time you open a door, turn a water faucet, or tighten a nut with a wrench, you exert a turning force. Torque is produced by this turning force and tends to produce rotational acceleration. Torque is different from force. Forces tend to make things accelerate. Torques produce rotation. So a torque produces rotation. Here are some examples: turning the doorknob, turning a faucet handle, or turning a wrench. A torque is produced when a force is applied with leverage. You use leverage when you use a claw hammer to pull a nail from a piece of wood. The longer the handle of the hammer, the greater the leverage and the easier the task. The longer the handle of a crowbar provides an even more leverage. A torque is used when opening a door. A doorknob is placed far away from the turning axis at its hinges to provide more leverage when you push or pull on the doorknob. The direction of your applied force is important. In opening a door, you push perpendicular to the plane of the door. A perpendicular push or pull gives more rotation for less effort. When a perpendicular force is applied, the lever arm is the distance between the doorknob and the edge of the hinge. When the force is perpendicular, the distance from the turning axis to the point of contact is called the lever arm. If the force is not at a right angle to the lever arm, then only the perpendicular component of the force will contribute to the torque. So torque is equal to the perpendicular force times the lever arm. The same torque can be produced by a large force with a short lever arm or a small force with a long lever arm. The same force can produce different amounts of torque. Greater torques are produced when both the force and lever arm are large. Although the magnitudes of the applied force are the same in each case, the torques are different. The first one, if you look here, the angle is a little different. It's not perpendicular, so you're not getting as much torque. In this one, you have perpendicular force, so you're getting more torque. This one, you get more torque because you have a longer lever arm. If you do not exert enough torque to turn a stubborn bolt, would more torque be produced if you fastened a long length of rope to the wrench handle as shown? No, because your lever arm is the same. To increase the lever arm, a better idea would be to use a pipe that extends it upward. How do you make an object turn or rotate? When balanced torques act on an object, there is no change in rotation. So we're talking about balancing torques. Children can balance a seesaw even when their weights are not equal. Weight alone does not produce rotation. Torque does. A pair of torques can balance each other. Balance is achieved if the torque that tends to produce clockwise rotation by the boy equals the torque that tends to produce counterclockwise rotation by the girl. What is the weight of the block hung at the 10 centimeter mark? So how would we find that out? So from here, it's gone, what, 10, 20, 30? So we're at 30 and 20. 30 times 20 is 600. So here we're at 10, 20, 30, 40. 40 times what will give me 600? The block of unknown weight tends to rotate the system of blocks and stick counterclockwise, and the 20 Newton block tends to rotate the system clockwise. The system is in balance when the two torques are equal. Clockwise torque equals counterclockwise torque, so force times distance, like I was showing on the other page, equals force times distance. So if you set this up and rearrange the equation, if you have FD equals FD, where you have force 1 and 2 and 2, you're looking for that other force. So force will be F2 D2 divided by d1, giving you the 15. Scale balances that work with sliding weights are based on balanced torques, not balanced masses. The sliding weights are adjusted until the clockwise torque just balances the clockwise torque. We say the scale is in rotational equilibrium. What happens when balanced torques act on an object? They're in equilibrium. The center of mass of an object is the point located at the object's average position of mass. This is kind of the key thing, average. A baseball thrown into the air follows a smooth parabolic path. A baseball bat thrown in the air does not follow a smooth path. The bat wobbles about a special point. This point stays on the parabolic path, even though the rest of the bat does not. The motion of the bat is the sum of two motions, a spin about this point and a movement through the air as if all the mass were concentrated at this point. This point, called the center of mass, is where all the mass of the object can be considered to be concentrated. The center of mass of the baseball and the spinning baseball bat each follow parabolic motion. You see the baseball follows this path, but if you look at the center point of the bat, where the center of mass is, it follows the same path as the ball. For symmetrical objects such as a baseball, the center of the mass is the geometric center of the object. For an irregularly shaped object such as a baseball bat, the center of mass is towards the heavier end. The center of mass of each of these objects is shown, so the baseball is in the middle, the bat is towards the heavier end, center of the triangle, center of the cone. Objects not made of the same material throughout may have the center of mass quite far from the geometric center. Consider a hollow ball filled with lead. The center of the mass would be located somewhere within the lead part. The ball will always roll to a stop with its center of mass as low as possible. The center of mass of the toy is below its geometric center. As an object slides across a surface, its center of mass follows a straight line path. If you see this wrench being thrown, the center of mass basically stays in one place as it spins around that. The motion of the wrench is a combination of straight line motion over its center of mass and rotation around its center of mass. If the wrench were tossed into the air, its center of mass would follow a smooth parabola. Internal forces during the explosion of a particular object do not change the projectile center of mass. If air resistance is negligible, the center of mass of the dispersed fragments as they fly through the air will be at any time where the center of mass would have been if the explosion had never occurred. The center of mass of the fireworks of the rocket and its fragments move along the same path before and after the explosion. When you throw a ball and apply spin to it, or when you launch a plastic flying disc, a force must be applied to the edge of the object. This produces a torque that adds rotation to the projectile. A skilled pool player strikes the cue ball below its center to put a backspin on the ball. A force must be applied to the edge of an object for it to spin. If the football is kicked in line with its center, it will move without rotating. If it is kicked above or below its center, it will rotate. You see in the first one, we have the straight line. If it moves off, he's kicking lower on the ball, so it will have rotation. Where is an object's center of mass located? It depends on the object.